Hi, and a warm welcome to our first day of the NCH Main Train event, Asia Pacific. The topic today is better performance, bigger savings for industrial lubricants. My name is Carrie-Ann Cleveley, and I will be your host for today. Before we get started, let me go through a few housekeeping items. So, you know how to participate in this event. We have taken a screenshot of the attendees page. Since we do have a large number of audiences online, everyone will be muted throughout the webinar. You have the opportunity to ask questions or send comments through typing in your questions using the question box of the control panel anytime during the presentation for our panelist. We are going to collect these and address them during the Q&A session at the end of the presentation. Okay, so let's get started. Here's a fun fact. Every year, it is estimated that 40 million tons of lubricants are consumed worldwide. Today, we're exploring the world of industrial lubrication and how the choices we make can have a big impact on productivity and efficiency. So, without further ado, I'd like to introduce our two presenters for today. Mr. Stephen Scarhill, our Regional Lubricants Director based here in Australia. Stephen has been with NCH over 10 years, leading and growing the local business in Australia, and more recently, expanding the lubrication model into Asia Pacific. Mr. Amano Brignolo is our technical manager, who has been with the business for 6 years, developing our lubrication business in the industrial sector. Amano has extensive experience in the field and holds a degree of engineering. First, let's view a brief introduction, 1-minute video, and then dive into our session with Amano.
Welcome everybody to this live webinar on industrial lubricants. Before we go into the real topic of this webinar, let me introduce NCH and tell you who we are, where we come from, and what we do. As you see here, NCH is a 101 years old company established in 1919 in Dallas, Texas, United States. Last year we turned $1.3 billion in revenue worldwide, and we distribute in all the continents. We manufacture our products locally where they are distributed. The products that we distribute are manufactured by us and developed by us. We have research and development to bring the products to meet the specifications, and then we have a number of corporate partners that we can rely on that will test our products in the field, so we can make sure that they not only meet the specifications that are relevant for the industries, but they actually do what our end users want. This allowed us to become one of the biggest independent manufacturers of lubricants in the world. Independent means we don't extract oil from underground, and we don't do fuel, but we manufacture a number of lubricants. And of course, we need to follow strict manufacturing specifications and rigid quality control standards. What we also like to do is to provide added value through a number of services that are complementary to our products, like oil analysis, fuel analysis, lubrication seminars, equipment reliability, value recognition reports, all designed to help our customers get the maximum out of the products they use and maximize the value. Now, the products that we do cover all the aspects of lubrication. Everything starts from greases and oils. That's the bulk of our business. We also do premium bulk oil improvers, but we also do fuel quality assurance products and services. And we have some specific products designed for specific applications, and also some application equipment to apply those products to your machinery. We work with a number of different companies that go from excavation, demolition, to concrete, asphalt, mining, quarrying, manufacturing, agriculture, up to something a little more demanding as well, like your food manufacturing, your steel mills, your refineries, paper mills. Pretty much everywhere there's a need for lubrication, we have solutions that can help. And now let's go into the real topic of this webinar, which is why we use lubricants and how we select them. First of all, the reason why we use lubricants is to overcome friction. And therefore, let's dig into this topic and find out what friction is. The picture that you see here is a magnification 350 times of a piece of steel that is as smooth as can be. If you look at it in real life, on the naked eye, it looks like a mirror. But if you put it under a microscope, all these little asperities become evident. And those asperities sliding onto one another will create what we perceive as friction. Friction is therefore defined as the resistive force that must be overcome when two sliding surfaces or rolling surfaces get in touch with one another. Now, friction is not always bad. There are some aspects in everyday's life where friction is actually pretty good. Without friction, for example, we cannot walk or we cannot hold a glass. However, in an industrial setup, friction typically is quite bad. Most importantly, its byproducts are quite bad. So let's have a look at how friction becomes a problem. First of all, there are three different kinds of friction. There's sliding friction that happens when two surfaces are sliding one across the other. There's rolling friction that happens when the surfaces are rolling one on the other, for example, when a cylinder rolls onto a table. And then there's a combination of these two, which is very, very frequent when you imagine, for example, of a gearbox. Now, there are a few factors that determine how friction is developed. There's load. The higher the load, the higher the friction. There is a speed. The higher the speed, the higher the friction. The finishing of the surfaces, the rougher the surface, the higher the friction. And also the hardness. You often have applications where you have two different materials, and definitely the softer material will always wear way before the harder one. And some components are actually designed with that very purpose in mind. So as we said, the problems are the byproducts of friction, which are wear and heat. So let's analyze how these happen and how we can handle them. Let's start with wear. Wear is divided into two categories. There's mechanical wear and there's chemical wear. Let's see the mechanical wear first. Mechanical wear, again, is divided into two categories. There's adhesive wear that happens when you have two surfaces in contact with one another, and the friction is so high that they actually become glued together. And then there's abrasive wear when you have three elements, the two original surfaces and some contaminants from the outside getting trapped in between and creating a lot of wear, as you can see from the picture. Now here you see three different examples of how mechanical wear can deteriorate your components. The first is a bearing truss pad, and you see that the excessive load has created a strange effect that has moved all the load-bearing material to one side. That means that all that material has adhered to another surface and has been moved from its original position. And then from the second, picture that you can see, you have journal wear caused by high-speed startup. That's another interesting aspect, because journal wear can be caused just because the oil is not able to support that load at the beginning, and therefore if you go too fast, too soon, you will have direct contact of two surfaces instead of having the support of the lubricant. And then we move to chemical wear. Chemical wear happens when some chemistry in the lubricant starts to deteriorate and become slightly different. And again, you have two different kinds of chemical wear. There's external chemical wear that happens when some contaminants from the outside get involved into the oil, for example, and start creating some unwanted effects like rust and corrosion. And then we have internal chemical wear. Specifically, we're talking about oxidation. Oxidation is a natural phenomenon. It happens when you heat up your oil and sulfur starts to get released in the air. And sulfur mixes very easily with oxygen, creating a gas. The formula is SO3, or sulfur trioxide. It's not a hazardous gas. It just smells funny. It smells like rotten eggs. And when you start smelling that, usually that's a sign that something bad is starting to happen in your oil. As I said, sulfur trioxide is not bad per se, but it mixes very, very easily with water. At room temperature, it mixes with water and it turns into H2SO4, or sulfuric acid. Now, sulfuric acid is really bad. First of all, it's very aggressive. It's highly corrosive. And also, it creates all those sludge, varnish, deposits and buildups that can create massive problems to your equipment. Now, I know that this sounds very complicated. To an extent, it is. So let's have a look at a video that shows how oxidation happens in real life.
And the first thing we're going to see are some bubbles. The oil is doing its job. It's trying to carry the heat away from the source. The second thing we're going to see are light wisps of smoke. This is the lighter fraction of the oil cooking off, going off through the catalytic converter and into the atmosphere. The tree huggers call this NOx and SOx. You and I might call this add oil. As these lighter fractions roll off, it leaves the medium and heavy fractions of the base stock, and then the oil starts to oxidize or thicken. But really, not a whole lot is happening to this oil outside of a little bit of smoke and color. But watch what happens when I add the contamination. Once that oil has expanded and contracted, it's lost all of its alkalinity.
So this is how oxidation happens on a very fast scale. Now let's see how we can detect oxidation and chemical wear problems in our equipment. These two pictures here show the effects of chemical wear. On the first one, on the left-hand side, you see some pitting, very localized pitting on a pinion. That localized wear tells me that this kind of wear is of a chemical nature, because otherwise it would be widespread equally across the surface. And on the right-hand side, it's very evident that the aspect of the piece of metal is absolutely different from what it looked at the beginning. So something really nasty happened in that side. This tells us that we need to be very careful on how we maintain our lubricants, and we need to keep them cool, clean, and dry. Otherwise, all the problems we mentioned before will start happening. Now, we spent a lot of time talking about oxidation, and we said that oxidation comes from heat, and heat is another byproduct of friction, as we said before. So let's have a look at how heat is developed in our system, where it comes from, and what it means and what it can create in our systems. First of all, we have 4 types of heat. We have ambient heat that comes from weather, and there's very little we can do about it. There's operational heat that comes from the kind of operations we're running. If we run a steel mill or or if there's a very powerful motor, then temperature is going to be very high. There's frictional heat, which is what we said before. It comes just from friction. When you rub 2 surfaces together, they will heat up, and that heat gets translated onto your lubricants. And then there's a heat coming from the load that you have. The higher the pressure between 2 surfaces, the higher the friction, and therefore the higher the heat that can be developed. And heat itself can also create some problems of its own, like a deformation on the metal. Metal can expand or contract at variation of temperature. And it can heavily oxidize some thin films of lubricant and make them adhere so strongly to the surfaces that you will need to either grind them away or replace the components altogether. So these are all the problems that the byproducts of friction can create to our system. And we said at the beginning that a lubricant is used to reduce friction. So let's see how a lubricant can do that. From a physical point of view, a lubricant is any substance that can create a barrier between 2 surfaces, and therefore it can separate these 2 surfaces from getting in touch and developing all the friction between one another. And therefore, by doing so, a lubricant also can cover a number of different roles in a machine. Let's have a look at what it can do. First of all, well, a lubricant is designed to reduce friction. All of them are involved in reducing frictions. The first line is quite obvious. There are some lubricants, though, that are specifically designed to absorb and dampen the shocks, and we are specifically talking about greases and gear oils. Some lubricants are designed to carry the heat away, and of course we're talking specifically about coolants, for example. Some others are designed to prevent rust and corrosion. Every time we see that RNO symbol on the drums or on the boxes, we know that there are some rust and corrosion inhibitors. That happens with almost every one of them. One lubricant is specifically designed to seal out dirt and contaminants, and we're talking about grease that can create a barrier around our equipment to shield away this kind of action. And there's also one lubricant, well, some of them are involved in this, but one specifically is designed to act as a flushing agent. So keep our system very clean and efficient, and that would be engine oil. Even though, admittedly, all the lubricants that go through a filter have a role in keeping the system clean. And finally, there's one of them that is designed specifically to transmit power, and that would be hydraulic oil. So at the end of the day, we are asking our lubricants to do a lot of things, and by doing so, we realize that they are crucial and critical in maintaining our equipment efficient, reliable, and highly operational. With that in mind, let's have a look at the process that we have in place to select the right lubricant and the right lubricant supplier. There are many options here that we all are familiar with. The first of which is use the cheapest available. Now, there's nothing specifically wrong with this, apart from the initial idea, which is reducing a lubricant to a commodity. And based on what we just said, which is heavy responsibility in keeping our machines going and our plant efficient, well, treating it as a commodity probably is not exactly right. And then there's the OEM recommendation. All the equipment that we have in our plant has an OEM recommendation about the lubricants. And there's nothing specifically wrong with it, again. The problem is that some of us are still running plants that are probably 10, 15, 20, even more years old. And therefore, that OEM recommendation has been written 10, 15, 20 or more years ago. That means that it doesn't take into account all the technological development that happened during these years. So let's have a look around and see if there's anything better that we can do to keep our machines running. The famous one, go with what's always being used, which translates into, if it ain't broken, don't fix it, which is fair enough. But I prefer to rephrase that into, if it ain't broken, don't forget about it. As we said before, there's always chance that we can do something better. So let's keep our eyes open for something that can help us achieve a better result. Use the corporate suggested product. That's another good one. Again, it's not necessarily bad, but sometimes, especially when we talk about big companies with big corporate office sitting in the CBD of the metropolitan area, sometimes it doesn't really mean that who is decided what lubricants we use has a real understanding on what the problems are right in the field where the lubricants need to do the job. Sometimes are just commercial agreements. So let's challenge the decision made at the corporate level and make sure that they actually do what we want them to do as end users, as we said before. And also, there's another one, which is testing the lubricants in our equipment until failure. Some companies like to do that, but some other times, some companies just want some equipment to fail in order to have somebody to blame. So probably that's not the real good strategy to select our lubricants. What really would make sense is the last point, which is evaluating technical data based on international standards like the ASTM, which stands for American Standards for Testing and Materials. So evaluate these kind of technical data and bench tests related to failed parts, and then make sure that the technical information that we have is really meaningful for the application we want and we need to handle. Now, once we have in place the right process to select our lubricants, we need to understand that there's one parameter that needs to be absolutely right. Otherwise, our selection process cannot be successful. Now, once we have the right process in place to select our lubricants, we need to make sure that the one single parameter that defines the function of our lubricant is right. The parameter I'm talking about is the viscosity. Viscosity is defined as the flow rate of a fluid at a set temperature, which is quite a complicated definition. More easily is the thickness of an oil. We need to have it right because it needs to be able to provide the protection that we want. If the oil is too thick, it will not be able to flow between narrow tolerances and therefore will not be able to provide the protection that we want. On the other side, if the oil is too thin and the two surfaces are distant enough, it will fall through and again will not be able to provide an adequate layer of lubricant. Now, there are a few parameters and few factors that define the viscosity that we need in our oil. There's a load condition. The higher the load, the higher the viscosity that we need in our oil. There's a temperature condition. The higher the temperature, the higher the viscosity. And there's a speed condition. The faster our system goes, the lower the viscosity needs to be. Apart from viscosity, there's another parameter that often is disregarded or neglected altogether, but it's very, very important in defining the performance of our oil. It is the viscosity index. Now, let me be clear on this aspect. Viscosity index is a number. There's no unit of measure, and it's a number that defines the ability of an oil to keep the viscosity within a certain range while the temperature changes. So the higher the viscosity index, the smaller the variation will be in the viscosity grade. Now, viscosity index is very complicated to calculate. You can see here a picture that shows how it's done. It looks very much like calculus because it is. It's very complicated, as I said, so we will not spend any more words in commenting on it. Just make sure that you understand that they are two different parameters. Now we finally go into the analysis of the base oils, which are the foundation of all our lubricants. And as we know, base oils are divided into two big categories. There are mineral base oils and synthetic base oils. So let's analyze for a moment the difference between these two. Minerals and synthetics are considered to be heavily different, and to a degree they are. But there's one word in common on these two definitions on screen that tell us that they come from the same product. And that word is petroleum. So both mineral oil and synthetic oils come from the petroleum that we dig out of the ground. And then the difference is going to happen afterwards when we refine them to different degrees to achieve a more or less homogeneous molecular structure. Now, what we extract from the ground, the crude oil, is of course not usable directly as it is. It needs to undergo a quite complicated process that we're going to see very briefly. Now, crude oil cannot be used as it is when it comes out of the ground. That's why we have refineries. They are those big plants with high towers and fires burning on the top of the towers. Crude oil goes into the plant, gets boiled up, and then the gases coming from that furnace get condensed at different temperatures. What comes out at 260 degrees from the atmospheric distiller then goes into the vacuum distillation process, and from that we extract all of our lubricants, our heavy oils, our light oils, our synthetics, and even some gases that then will turn into lubricants again. And then what comes out of the vacuum distillation is divided into groups or categories based on two parameters, the sulfur content and the viscosity index. And these are the differences between our minerals and our synthetics. We have 7 groups of lubricants, of base oils. Groups 1, 2, 3, so 1, 2, 2 plus, and 3 are typically our mineral oils, which have a relatively low viscosity index and a high sulfur content. And then group 3 plus, 4, and 5 are our synthetics. Very difficult to make distinction between groups 3 and 4, but the important thing is synthetics are all with a very high viscosity index. And again, let me stress out that they all come from petroleum, from the crude oil. Now there's a sort of a myth or a common conception that synthetic oils are always better than minerals. Let's see if that's exactly true. There are some distinct advantages in using synthetic base oils. Now there's a common understanding that synthetic oils are always better than minerals. So let's have a look if that is really true. It is true that there are some advantages using synthetics, yes. Specifically, synthetic oils have a improved thermal and oxidative stability. because they have a higher viscosity index. And they also have a higher viscosity index because they have a higher viscosity index. So this is a bit of a loop. And finally, they have improved extreme temperature properties because they have a higher viscosity index. On the flip side, though, they are also very expensive because it's much more complicated to process them and to refine them. They do not provide the same lubricity as mineral oils, and they cannot use some performance additives that are crucial for some operations. And finally, they tend to emulsify with water very easily. So you need to keep them extremely dry. Otherwise, you will have a nice pot of milk instead of a nice reservoir of oil. And finally, let's have a look at the volume of lubricants that come out of a refinery. Just to have a quick idea, if you look at this picture here, the lubricants are the tiny little purple slice that is less than 1%. So all coming out from the crude oil goes into different applications like your plastics, your asphalt, bitumen, gases, fuel. Fuel is the vast majority of it. Lubricants are the tiny little slice that for some manufacturers is necessary evil. And now out of that 1% that comes out of the refinery as base oil, we can manufacture different kind of lubricants. If it's just base oil plus some additives, we have our lubricating oils. And if we have base oil plus the performance additives plus a little bit of thickener, we have greases. Now we all know that if we take a grease cartridge and we turn it upside down, hopefully nothing happens. And that's because of the thickener. And with this in mind, the fun fact is that the percentage of the thickener inside a tube of grease is something between 2 and 3%. That's more than enough to turn your oil into a grease that can stay attached to a surface without slinging off. The most important aspect and the most important components of our lubricants, though, are the performance additives. So let's have a look at what these performance additives do. We have 4 categories of them. The first are friction-reducing agents, friction and wear-reducing agents. There's oxidation inhibitors that are designed to handle the oxidation process. There's rust and corrosion inhibitors that are designed to handle the external wear. There's acid neutralizer, there's anti-wear and EP additives that we see in our gear oils, and there are shock load reducers in our gear oils and greases. Then there are some additives that are designed to handle the temperature problems. So we have the pour points, depressants, and viscosity index improvers, and there's in greases specifically we have the heat reversion thickeners, your aluminum complex, for example. Then you have your solid additives, your moly, graphite, Teflon, calcium sulfonate. These are in a solid form. They are typically powders. They get mixed into the grease to help the lubricant withstand higher load conditions. And then you have your functional additives that specifically handle problems that are related to some functions. For example, seals conditioners, leak inhibitors, adhesive and cohesive polymers, your detergents and dispersants in your engine oils. All these additives make the difference in the performance that your lubricant can provide, and therefore will deliver a much better quality in the lubricants and a much more reliable workability of your machines. Finally, let's have a look at the family of the lubricants that come out of this process. You have your greases that are designed to seal out dirts and contaminants, protect, and lubricate. You have your gear oils that have the added function of cooling. You have your hydraulic fluid that need to transmit power, but also needs to cool some system, and they need to protect your parts. Motor and compressor oils that act, as we said before, primarily as flushing agents. You have your surface lubricants like your moly, your dry lubricants, your Teflon, your open gear lubricants, your anti-seize. And then you have your penetrating lubricants like your chain ropes, your Y ropes lubricants, your release agents. Finally, let's have a look at how the lubricants have a direct impact on your maintenance costs and potentially your maintenance savings. The graph that you see here is an average snapshot of what the maintenance costs look on average in a manufacturing company. Now, let me be clear, there's no one company in the world that has these numbers exactly. This is an average that comes from an investigation we did on well over 100 customers of ours. And we have found out that before they switched to NCH, the cost of lubricants was 2% of the total. The labor cost, so the labor associated to handling breakdowns and downtime, was 26%. 20% was the actual cost of the downtimes, 30% was the parts replacement, 1% is the waste oil, and energy and fuel consumption summed up to 21%. Now, the interesting part is noticing what happened to these companies when they moved from standard lubricants to advanced performance lubricants. The first thing to understand is that none of the slices disappeared. We still have labor costs, so nobody lost their jobs because the company went to better lubricants, but the incidence of those costs on the maintenance was reduced from 26 to 23%, saving 3 points. Same thing happened to downtime. It didn't disappear, but it was contained from 20 to 14. Parts replacement, same thing, went from 30 down to a whopping 22%, so saving 8 points. Waste oil remained pretty much unchanged, and energy and fuel consumption went down from 21 to 18%. The only slice that grew a little bit is the lubricants cost. What that means is that by investing a little more with lubricants and moving that slice from 2 to 3%, these companies have been able to save 19%, which on a total of $400,000 a year, it means $76,000 saving just because they adopted better lubricants. Now, at this point, we understand the process to select the lubricants and the implications of that choice on our maintenance costs. So let's have a look at a real-life example of how the right lubricant can make the difference in the performance of our equipment.
So you just heard from Emano on some of the theoretical side of things with the slides, why we use lubricants in the first place, some of the common issues that I'm sure most of you face, and also why we use higher performance lubricants and what benefits they can have. What we'd really love to do now is show you more of a live demonstration, one of our key products, our Primolube grease, our #1 selling lubricant. And we want to show you a couple of live tests around 4 main areas. One of them is heavy load conditions, the second being heat, and the third being contamination of water and airborne particulates. So, and you can see we have a contraption here. This is related to a heavy loads environment, and Emano is about to show you the grey grease is our Primolube and a Brand X competitor's grease, and how they perform under a high load condition. So Emano will start. So we can see straight away quite a clear difference. If you zoom in a little bit, I'm also going to just pull this away, and quite evident you can see the difference where the Primolube really stayed in place. The other grease has really splattered out, and you can see the steel exposed, so that not performing to lubricate where the metal to metal contact is. And if I take a little bit of the product, put it in my finger and just move it up and down, you can see the reason it works so well is it has adhesive and cohesive polymers. Adhesive sticks to my fingers or sticks to the metal. Cohesive sticks to itself. And that really helps the grease stay in place under a high load condition. So the second test we're going to look at now is for heat. So we're going to stress test the grease with high heat with a little butane torch. And again, we have the Primolube grease and our competitor's grease, and Emano is going to put this demo to work right now. So we're melting the Brand X grease first. And you can see quite quickly the grease melting off. dripping. And then we work on the Primlube grease. Same conditions, same amount of heat. What you'll notice straight away, it takes a little longer for the grease to melt, but it is designed to melt above the threshold temperature. So now it's starting to melt and drip off. Okay, great. So if we get the camera in here, we'll show what we're most interested in is the grease that has melted. So if you look closely, you can see, hopefully you can see, it looks a little different. The brownish grease has gone more like a candle wax kind of consistency, whereas the Primlube grease has remained still the same grease as it was before, the sheen and everything on it. If I then, now that it's cool, just dip my fingers in both of them, you will also see that the Primlube has retained the tackiness and the brown grease has kind of lost a lot of that stickiness. So what we have unique to NCH Primlube grease, or unique to an aluminium complex grease, is what we call heat reversion. So the grease, once it lowers below that threshold melting temperature, returns to its original state and is still good to be in the bearing and in the same condition to help reduce the consumption of grease. So our last issue is contamination. We talked about two types of contamination that most everyone has to deal with. First being water or wet environments. So we're going to get Amano to show you how this works with our Primlube grease. Okay, so we're just going to take some of the Brand X grease to start with, pour water, and he's going to rub it together to attempt to mix the grease and water together. And what you can see happening fairly quickly, it's pushing away from the point of contact, the finger. We saw that in the first test for load. But secondly, more importantly for this, you can see it really lightening up, going more of a milky colour. We often see this with oil. I'm sure you've seen a milky oil. The same thing happens with grease, and you can see that happening, and that's emulsification with the grease. So now we're going to do the same test with the Primlube grease under the same conditions. So we'll grab a sample of the Primlube in the palm, same amount of water, and attempt to do the same thing and mix the water into the grease. Give it the same amount of time. And what you can see straight away is grease is more resistant to being pushed away from the pressure point of the finger. You can see less of his palm. Okay, so you can see that now the grease hasn't changed colour, it hasn't absorbed the water, so we call it hydrophobic. We have some graphite as one of the additives we put into this grease, and it helps to make the grease very water resistant, so it lasts a long time in wet environments, as you can see. Okay, so our final demonstration is around contamination, our solid contamination. So for an example here, we have a pile of sand. This could be sand or dirt or grit that gets into the grease, forms what we call more of like a liquid sandpaper. So Mano's going to show you a little demonstration how we show this. So we take a dollop in each index finger, the Brand X and the Primlube, dip it into the sand contamination here, and then really rub finger and index finger and thumb together to mix the grease and the sand together. This one is a little difficult without, normally we get our customers to do this to feel it. But what's happening here, if you can sort of reveal, Mano, with the brown grease, typically, and I did this one before, so I know the feel. It feels sharper. You can feel the sand grits much more. With the Primlube, the sand will stick to grease. Grease is grease, and the sand will stick. But with Primlube, it tends to coat. The additives will coat the particles of sand or dirt, and it softens or lessens the grinding impact. So that's why it feels softer on the fingers, and therefore in the equipment it has less impact for wear on the equipment. Okay, so that's the demos we wanted to show you. Thank you, Amano, for the products, and I'm sure you can see quite clearly illustrated the difference between a premium grade grease and a more generic grease with our Primlube. At NCH, we're very aware of the day-to-day issues and problems that our customers face in the field in real life, and all our products are designed to combat those problems. End result really being in particular for grease, a reduction in consumption, Also, more importantly, the larger savings opportunities around reduced downtime, labour costs and parts replacement. So thank you for watching.